Professor,
Yes.
does the review for the midterm have everything that will be covered on the midterm itself?
I always guarantee at least 80% of the points. So if you took it an infinite number of times and memorized every right answer, you should get no less than an 80.
Okay, thank you.
It turns out to be 100, but it's at least 80.
Okay, so are part of the questions from the review itself used on the midterm or similar
Yeah,
questions?
that's what I mean. At least 80% of the points on the actual midterm are accessible through that practice test.
Oh wow, thank you.
No problem.
I also had a question about that. What resources are we allowed to use for the midterm?
You're allowed your equation sheet, which can be front and back. The main thing is it only can be labeled equations and ones that I explicitly told you, like for instance, that equation I gave you the other day about conservation of energy. That's not one you'll find in your book, but you're certainly allowed to include that.
Okay, so things that you've given during lecture, basically.
Well, I made statements throughout the semester telling you this one's not in your book, but you can use it. Other than that, it's just the labeled ones. But I don't think I've said that but a couple of times, like when I made the gravitational equivalent of Newton's law of gravity with vectors. That was one that was you'll not find the exact same form in your textbook. But you can use that. And the conservation of energy is the only other one that I'm thinking of right now.
All right. Is that like a formula sheet that we put together, or is that on like the? Oh, okay.
Yeah, it's one y'all put together. Just because I've put a lot of time into trying to make them, and they always go to crap. Like I'll get an email saying a student opens it and it won't show the equations or something, so I stopped trying to make them.
I gotcha. What about the same equation, like kind of rearranged? Like I have a couple of equations written down here for like the geosynchronous orbit section, like for period and radius and stuff. I have a couple of those rearranged just for convenience, I guess. Is that okay?
No, it should be only in the form that you see it in the book, unless I gave you, like I said, unless it's one I explicitly told you. In other words, you probably need to solve for that or rederive it or something like that on the test.
Well, I mean, it's not like I don't know. It's not like, well, I think these were ones that you gave us. I don't remember if this was something that you specifically said is okay to use.
Can you show me the equation or read it to me?
Yeah, here. It's that one. Can you read that?
Oh yeah, 2 pi times the square root of, what is that? I can't read it. It's in the square root.
It's 2 pi times square root of radius cubed over gravitational constant times mass.
Yeah, that's just another form of Kepler's third law. So yeah, I don't mind if you use that one.
Yeah, so that's what I was talking about. It's like formulas that you've given us, but we just rearrange it to find for a different variable in that same equation.
Yeah, I would say as long as it has the original symbols in it, then that's fine. You're just saving yourself a couple algebra steps, so that's okay.
Okay. How can we tell which ones are and aren't allowed?
You just like looking at the textbook
of the things that you've given us.
Hopefully you wrote it down when I said y'all are allowed to use this, even if it's not in the book. If you haven't, then it's only the ones that you can I can remember or that have a number by it.
I mean, I write down whatever formulas I can catch in your lecture because they're almost always useful. So yeah, I don't have anything written down as far as like this one can be used on tests and this one can't.
Right. So what I told students throughout was, like, if you look on page 170, there is a equation Fs equals negative Kx, and it's got a parenthesis 7-8 close parenthesis. All of the equations in the book that have those parentheses, chapter number dash something, all of those are fair game. I will tell you the only two that I recall doing, giving you the permission to use, even though they're not in the book, are labeled in the book, is that U initial plus K initial, kinetic energy initial, plus work in equals U final plus KE final plus work out plus E loss. That's one. The other one's that gravitational form, or that vector form of Newton's law of gravity. That's the only two that I definitively know I've told you guys.
Okay, so what do we like if I were to put together a formula sheet, and then I guess you would take a look at them before we
Yeah,
start the
one of the
test?
jobs is when you do on the video monitor is it asks you to show your workspace environment, and what you have to do is hold up a piece of paper and so that I can read it, and then turn it over and then show it to me again. You also have to do that with a photo ID and your own face. You also have to use your camera, your webcam to show, the lungeable space around you. In other words, what can you lunge to reach during a test? So any sheets are on the board, you're gonna have, that you have on the desk are gonna have to be shown front and back. You're allowed to, I told some students you can make copies of the inside, front, and rear covers, but a lot of you have binder ready books or you have the ebooks. You can print those out or take a, or pull them out of your binder ready book and use those. So anything in the front or back covers of what would normally be a print textbook. So basically, any of the constants that we use, you can write those down. The mass of an electron, the charge of an electron, the mass of a proton, the mass of the earth, mass of the sun. But normally with stuff like mass of the earth, mass of the sun, we'll give you those if you're asking something about it. Prefixes, SI prefixes, you're allowed. Mathematical formulas like derivatives and integral formulas, they're okay.
Okay.
And you do need your calculator, and it can't be the one on your phone.
Yeah, I guess I got to get my hands on one of those because I've been using an online calculator for the most part with like homeworks and stuff.
Yeah, the browser is going to be locked down, so you won't be able to use any other resources.
Gotcha.
Professor, is a
Yes.
TI-84 allowed, or is
Yeah.
it just a? Oh, okay.
Yeah, I allow programmable computers and everything. It's not, calculators and everything. Nothing that has access to the internet, so you can't use one on your iPad or something.
And
Because that's a video screen that you could have access to the internet with.
what is the more recent ones like TI-90 or something?
Yeah, the TIs, they're in the 80s are plenty good. You can certainly get a newer
Maybe it
one
was a
if you want it.
TI-89 was the one I was thinking.
Yeah, I think there's even a higher. I've got a TI Inspire, which is super fancy, but it's actually so fancy that I don't like it. Like you have to hit a couple buttons to get a trig function now, and that's just stupid. A bunch of weird things like that. Sometimes the simpler is better, but I like a big screen. That's the only thing. So my favorites is the HP calculator. I have an HP 48G. That's my favorite, but it's in that RPN. They call it reverse Polish notation, which I'm pretty sure is insulting to Polish people or something.
What is the? Do you know what the difference is between a 84 and 84 plus?
It usually has some extra programming capabilities, and it might even graph like in 3D or something. But I wouldn't waste, if you're going to be an engineer, I wouldn't waste a whole lot of money unless you are going to be an engineer, and then it'd probably be worthwhile. A physicist or an engineer, it'd be worthwhile to have one good calculator. That's, when I bought mine was when I was in probably a junior in college.
Yeah. It looks like
are good. The Casios are good. The HPs are good. I prefer HPs myself, but you don't want to try to learn how to do that the day before the test.
Yeah. It's kind of expensive, but it's not awful. You can get an 84 plus from Walmart for 90, it looks like.
Yeah. And you can even find, if you don't want that fancy, you can find them probably all day long that have enough for this test. You can find them for $10.
Actually, wait, what?
Yeah.
What for $10?
I've seen them at Food Line, like just a scientific calculator. If it has a sign button on it and a way to put in scientific notation, that's really all you need. So I've seen them as cheap as $10 at places like that.
Yeah, I guess that's true.
But like I said, maybe the next one might be a good one to, after you finish this midterm, maybe throw some money into a nice calculator, but maybe not for this midterm.
Gotcha.
You'll have a better feel for what you like and stuff. I use mine. You can do all the things that Desmos does with a good calculator. So that's nice to have right at your hand. Anybody else have any questions?
Sorry I joined late, so I don't know if it was already asked, but I was wondering if the midterm was more based conceptually or like on calculations.
We have more or less, you're going to have at least probably 4 to 6 concept questions, and then it's going to be like 6 working problems. But I give you like 2 hours.
And is it like free response? Because like I didn't know if it was like a multiple choice thing online, or we're submitting
No,
like a file.
sometimes, and I'm not telling you whether I did or didn't, but sometimes I'll have a problem where you might have a free response and you're supposed to take a photograph of your work and email it to me within 15 minutes of turning in your test. But sometimes I'll just have a multiple choice and have you show me your work as well. Not saying that is or is not the case this time. I'm just saying that's the only other possibilities. But I generally try to stick to multiple choice because I have so many students. You see how long it's taken me to grade labs. You can imagine how much of a nightmare it is to grade handwritten tests and stuff. So yeah, most of them are multiple choice. Any other questions? Well, we really had finished chapter 8, but I wanted to show you a couple more types of examples you might encounter. And I think that's a worthwhile thing to do. So I'm going to do those, and that's pretty much all I'm going to do for today. Next time we'll jump into chapter 9. I think after 9 is when I can jump to relativity. I can't remember if it's after 9 or after 10. So just keep an eye on that. Does anybody have any other questions before we get started?
Said the midterm was a 2-hour time limit.
Yes, that's why I
Okay.
mentioned to everybody, this class is supposed to start at 11. I can let you start, like, you know, since it runs supposed to be basically till 11:50. I can let you start as early as, let's say, 11 a.m. or 10 a.m. so that you can fit it in the 2 hours if you can go all the way to noon.
I mean, the only thing I have specifically is just the lab at 1, so it should be fine.
Yeah,
I was
I
curious
also allow
about
you
that.
to stay up to an hour late. So I open the test basically an hour early, and then I close it an hour late. So you've got, if you start late, you're going to be screwed because you know, you're not going to get your full 2 hours, and that's not my problem. So make sure you guys start at least by 11, or you won't get your full 2 hours. And no one sent me
Gotcha.
any accommodation, so I won't be honoring them because you haven't given me enough time now. Now, that being said, would you guys like to push that to Monday, or are you still good with it on Wednesday?
No,
During
Wednesday's
class
fine.
at 11, you said?
Class starts at 11. You have a 2-hour test, so that means you need to be able to work until 1 to get that full time, or start a little early and work and finish a little early. So like if Gavin has a lab at 1, he might want to start at 11:15 so that he can be finished by 12:45.
Okay,
Professor?
cool, because I have your lab too.
Did you
Yeah.
say we have an option to push it till Monday?
Yeah, I'm willing to do that for the entire class if you are interested. I felt bad because I had some problems with the practice tests and I had to rework them a couple times. So I'm willing to push it back to Monday per class. So like if the majority of you wanted to.
Yes, let's go to Monday.
I think
would
Monday's
also
fine
for
because
Monday.
we still
A
had
lot
to
of
finish
votes
chapter
for
8 a little
Monday.
late.
Okay. How about you, Gavin? You cool with Monday?
Yeah, that's fine.
Yeah, it looks like most people are wanting Monday.
I-
I'm completely cool with moving it to Monday. You guys meet Monday, Wednesday, and Fridays. But I do like a test either on Friday or Monday anyways. So I could move it to Friday or Monday, but I think Monday might be a better choice for you guys because I really want y'all to take it seriously. I really get disappointed around the midterm. A lot of people average in the 50s. So
It would, yeah, I'd be able to get my hands on a better calculator and kind of get used to it by then. That'd be nice.
all right, we'll put it off till Monday, everybody. So,
Also, you said you kind of fixed up the practice test because
mhm.
it had some weird questions on it.
Yeah,
I
it
still
should be
ran
fixed
into
now.
a question about light bending around the mass of the Earth.
That was from the general relativity explanation I gave you guys. So that actually probably is a fair question. I
Was
don't
that?
remember it off the top of my head.
Like
That's
light being affected by gravity. I don't remember taking any notes on that.
yeah. When I gave you that last bit, I basically did one whole lecture about what Einstein did, and then I went into general relativity and showed you how, in fact, gravity is no longer really considered a force. It's basically gravity we recognize now is not a force. It's more of a bend in 4-dimensional space-time that causes things to move in ways that they otherwise wouldn't. Just like an ant, you know, tries to walk straight around an apple. And since the apple is curved and dented, it's going to go up and down and end up going in a circle. That's what the planets are doing. They're actually going straight, but the space is bent like a surface of a trampoline with a bowling ball in the middle.
Is there a bit in the book, I guess, in the text about that?
Yeah, that should have been. Yeah, that and I did
Or I
post a
guess if
lecture
you
on my.
know Yeah, I was gonna say, if you know what lecture it is, I could go and take a look at that because I don't remember that at all, actually.
Yeah, it says Introduction to General Relativity and Cosmology, and I think there's like 2 or 3 versions up there. Far as it was in chapter 6, what your book talks about, and it starts on page 6-8. So
Page 68 in the text.
section 6-6 and section 6-8 are really what it's talking about. First, they introduce the gravitational field, which sort of answers your question about the matter not having a force on it if it's inside the spherical shell of gravity. That's what 6-6 is about. And then 6-7 and 6-8. 6-7 prepares you, but 6-8 is actually talking about general relativity. But I gave you a more thorough introduction, not only to general relativity, but also to the Big Bang, cosmology, all that stuff. If you look at my list, it should be up there too. Like I said, I think the all is introduction to relativity.
Do you think that was the day? There was one day that I showed up because for some reason I thought class started at noon.
That could be it, because it was like a Friday, I think, was the last day.
Oh, okay. I do have one class that is noon to 1. I think I mixed it up with that, but okay, thank you.
Yeah, no problem. All right, so it looks to me like the majority of people voted for Monday, so we'll go ahead and push the test back to Monday. I don't mind that at all. And actually, that's more consistent with our week number. So just be prepared to do the exact same thing Monday, but also be prepared. Remember, you guys are going to get 2 hours. So that means you got to either prepare to start an hour early or to finish an hour late, or maybe start 15 minutes early and finish, 45 minutes late. But if you start later than 11, you're not going to get 2 hours, and that's on you. So I don't want you guys to do that. But the main thing is the online version of a midterm often makes my students class average go down a lot because it counts a lot. And 2, you're not allowed to do internet searches. Some students lean on the internet searches more than they realize. They lean on their notes more than they realize. And that's why I'm, trying to be really nice and try to make sure you guys do well on it. The good news is once you get that, you get a final exam that's going to be just like it. So you get another poke at improving it. So if you didn't learn by the midterm, you will have a chance to regroup and learn by the final. All right. All right. So we want to solve some problems now. And I wanted to give you some ideas of how to solve problems like gravity problems, conservation of energy problems, that sort of thing. So what I'm going to do is I'm going to imagine a person hitting a ball off of a cliff. Let's say he's actually hitting a golf ball. So we'll say a cliff like this, and it drops down really, really far. Let's say H is equal to 100.0 meters. Oh, y'all probably want to see what I'm writing, don't you? Y'all not interested in looking at the top of my head, maybe? By the way, Gavin, I have that same shirt. I love it. It's great.
Yeah.
All right.
I think I got this as like a Christmas gift a couple of years back or something. It's a pretty good shirt.
It got me in a little bit of trouble. I was at my physical therapist after my shoulder replacement, and they saw my shirt and they assumed I was watching Game of Thrones, which I hadn't watched it at all. And I'm not that good at hearing, so I often agree to things without knowing what I'm agreeing to. So it basically was like 4 weeks of really intense stress because he kept asking me questions about the show, and I was like, I didn't. It was too late to admit that I didn't watch it. So, all right. So let's imagine a golf ball is hit from a cliff, and let's imagine it's hit at say 37 degrees with a velocity of 25.0 meters per second, and we'll say that's 37.0 degrees roughly. I would like to know. It's going to do this, right? And it's going to land way over here. Okay. I would like to know H max and the speed it has here. Okay. And I want to do this with conservation of energy. So my normal equation, the one I told you guys you're allowed to use on the test, even though it's not in your book, is potential energy initial plus kinetic energy initial plus work put in is equal to potential energy final plus kinetic energy final plus work out plus E loss. Again, that's just, and you can add more terms to this, like I said, if you want to. The main thing is you got to account for each type of energy put into the system or taken out of the system. If it's taken out of the system or work done by the system, then you put it on this side. If it's work put into or energy put into the system, you put it on this side. So you might have 12 different things you can put in here, and therefore you'd have like, you know, maybe 5 terms over here and 7 over here or something. All right, so first off, I want to know what its max height is. Well, that's pretty straightforward. All we really need to know is, you know, what's its potential energy. So basically, we have a potential energy final that's mgh, or excuse me, initial that's mg lowercase h, and then we have a potential energy final, which is that guy, right? So in kinematics, we would go ahead and take the vertical component of velocity and see what that gives us. And you could do it that way. You could say VF is equal to V0 plus AT. That would give you how much time it takes to get to a 0 vertical velocity. So you could say VF, and I'll do this really quickly just to show you that we get the right answer. So V final is 0. And we'd say that, of course, since that's 37 degrees, that's opposite the 3. So that'd be 15 meters per second. That's the vertical component. Basically, I'm doing the 3, 4, 5 triangle, and 37 degrees is opposite 3. This would be 4. This would be 5. Obviously, to get 25, I have to multiply 5 by 5. So obviously, I have to multiply 3 by 5. That's why I got 15 meters per second. 0 is equal to 15 meters per second plus negative 9.80 meters per second times t. That gives me t is equal to basically 15 meters per second, which should be 3 sig figs, by the way, divided by negative 9.8, or excuse me, positive 9.80 meters per second. If I did that just quickly using kinematics, like I said, that'd be 15 divided by 9.8, and I get 1.5306 seconds. Now you have to do is figure out, okay, well, how far would it go in that time? And that's just the x equals 1/2 AT squared plus V0t plus x0 if you wanted. Okay, if I chose this to be the origin, then I just have to add 100 to whatever measurement I got, or I could choose this right here to be the origin, and my initial height, of course, would be 100 then. So I'll do that second just to check. So what we're going to do is say x is equal to 1/2 negative 9.80 meters per second every second. Forgot that on that part. Times 1.5306 seconds squared. Now that was minus because we're using up as the positive direction and down as the negative direction. So this will be plus 15.0 meters per second times 1.5306 seconds plus 100.0 meters. So we can then say x is going to be equal to, let's do that,
Sir,
0.5.
what was the initial velocity again? Is that like 25, 35, something like that? I couldn't read.
The vertical component would be 15 meters per second. And that was because the velocity, remember, was actually 25, but it was at 37.
Oh, it was 25.
Yeah.
I didn't get that part. Okay.
Yeah, that's the total velocity. That's the muzzle velocity, if you will. So I'm going to say
Okay.
1/2 of negative 9.8. Well, actually, I already wrote that out. I don't need to write that again. So I'm just going to do 0.5 times negative 9.8 times the time squared plus 15 times the time plus 100. And this gives me 111.47. Actually, I should say 48 meters. So that's the max height. If we just did it with kinematics, now what we want to see is what we can do with kinetic energy and potential energy. Okay. So the potential energy initial is actually mgh. Remember, that's sort of our general formula for kinetic, for potential energy is mgh. We don't know what m is, but that's okay. So I'm going to take the initial kinetic energy, or potential energy is going to be m times g times the h, which is at 100 meters. Okay. The initial kinetic energy is actually going to be equal to 1/2 mv squared. And that is the whole 25 meters per second, right? Now that's the only two forces. We're not talking about air resistance or anything like that. So we're not talking about anybody applying a force to speed it up or anything. All we're doing is analyzing it the second it left the head of the club, which should be at the 0 height on the cliff. So the next thing we do is the final potential energy, which would be mgh max. But we also still have a kinetic energy, 1/2 mv horizontal squared. In other words, when it gets to that max height, it's still going to have a velocity. And in fact, we're going to have to figure out what that velocity is. So when it reaches that velocity, or that point right there, notice its velocity by default has to be horizontal. And since we're ignoring air resistance, there is no acceleration horizontally. So this must in fact be 4 times 5 or 20 meters per second. Okay. So that's how we're going to account for this, and all the other terms are 0. So I have no work in, I have no work out, I have no E loss. So now all I'm going to do is say that if I want to know H max, first thing I can do is realize that all the masses drop out, which is good because I didn't give you the mass of a golf ball. So that m, that m, that m, and that m are all dropping out. I'm solving for H max, and I'm going to say that's equal to GH plus 1/2 V. And I maybe should put a 0 there just to make sure everybody knows I'm talking about the initial velocity. So 1/2 V0 squared minus 1/2 VH squared over G. So in fact, you can simplify that a little bit and just say it's H plus 1/2G times V0 squared minus VH squared. And you'll notice that looks a lot like our kinematic equation. V final squared equals V initial squared plus 2A times the change in height or change in position. That is exactly the same result we got kinematically. And now we can calculate it. So H max is going to be equal to the original height, which is 100.0 meters, plus 1/2 times 9.80 meters per second every second, times the initial velocity was the full 25.0 meters per second squared, minus the velocity at the top, which I argued was the horizontal velocity that the thing had initially, which is basically 25 times the cosine of 37, which I'm arguing is basically 4 times 5 or 20 meters per second. So 20.0 meters per second squared like that. So I can now get hopefully 111.48. So let's see, 100 plus parentheses 25 squared minus 20 squared divided by parentheses 2 times 9.8. And that looks like everything I need. The units, meters, this is meters squared per second squared divided by meters per second squared. So that is going to give you just meters. So I get, whoa. Oh, I did something funny. I typed in a multiply and then a subtract. So that was the problem. 100 plus parentheses 25 squared minus 20 squared divided by, again, I'll use my parentheses, 2 times 9.8. And this time, why is it doing that? It keeps giving me that multiplication in there instead of that.
So on that equation there that you have pointing to like 20 meters per second, pointing to the
Right.
V, that's VH for V horizontal.
Yes. That's correct.
Okay.
Okay. So I'm just, for some reason, my calculator is doing something funny. That's what I'm telling you about some of these new calculators. They really make things kind of bad. This 25 squared minus 20 squared actually turns out to be 225. So I'm going to divide that by 2 times 9.8. And I get 111.47. And then of course 100, that gives me 111.48 meters, which is exactly what we got before. You can see where the 100 or the 11.47, which I called 48, came from. Any questions on that? So it's not that you're completely getting rid of all the vector stuff. Sometimes you still have to deal with the vector-ness of initial velocity. Sometimes it's not quite that hard. In other words, if this was just a ball going straight up and down, it wouldn't have been a problem at all. We wouldn't have to do any components of vectors. But since this was a horizontal and vertical motion, we had to take into account the fact that the object actually had a final velocity even at the top of the motion. It's just that velocity was horizontal. So this was part A. What we want to know now is what's the speed when it gets to the ground level. So now I'm going to do again, U initial plus kinetic energy initial equals U final plus kinetic energy final. So I've got mgh plus 1/2 mv0 squared is equal to mg times 0 plus 1/2 mv final squared. Okay, now this doesn't give me the magnitude or the direction or anything. It just gives me the magnitude of the velocity. But again, I can cancel out the masses. That was 0 anyway, so I don't have to think about that. And from this, I can get v final is obviously equal to, I'll multiply through by 2. It'll be 2 mgh plus, or excuse me, 2 gh. I forgot I got rid of m's already. 2gh plus v0 squared, and then that's it. Take the square root of that, which I think you can see again looks like that v final squared equals v initial squared plus 2g times, or 2a times x minus x0. So we can compute this. We get square root of 2 times 9.80 meters per second every second times 100.0 meters plus 25.0 meters per second quantity squared. So I'm going to do 2 times 9.8 times 100. Now I'm going to say plus 25 squared. That gives me 2,585. Now I'm going to take the square root of that. Dang it. Okay, sorry about that. So I get 50.84. 843 meters per second is my final velocity. Of course, I should only be using 3 sig figs.
Move the paper up a little, please.
Yeah. If
Thanks.
I'm thinking of this right, how this added out, I should get only 3 sig figs. That should be V final. Okay. So I hit it at 25 meters per second, and it's actually going to hit the ground at 51 meters per second. If you really wanted to break that down into vectors, all you got to realize again is that this horizontal component is going to be 20.0 meters per second. And this right here is the 50.843 meters per second. So you could get this angle and everything if you wanted. Obviously, this is opposite over hypotenuse. So theta equals the inverse sine of 20 over 50.843. So 20 divided by that, and I get 23.16 degrees. Below the horizon. So in other words, actually that's above vertical. So 90 minus that would be the angle from horizontal down. Okay, so that's just this angle. So again, you could actually get back all the information you had from kinematics again, but you have to use some vector stuff to make sense of that. Anybody have any questions on that problem? All right. So let's go ahead and do another problem. Again, I'm assuming no one has any questions on that, right? Everybody follows what we did. Are you able to see it well enough, or do I need to zoom in and show you some numbers or stuff? Okay. All right, so now I'm going to use that gravitational potential energy thing that I did earlier. Remember, we found that work is actually equal to the negative change in potential energy, or change in potential energy is equal to the negative of the work. So what we ultimately found is that the potential energy due to gravitational force is negative G, the mass of the body, times the mass of the planet over R. So that's the true potential energy. If you're dealing with heights that are comparable to the radius of the Earth, you need to use this, not MGH. Okay, so we can use that. Again, we have U initial plus kinetic energy initial plus work in equals U final plus kinetic energy final plus work out plus E loss. Again, that's my version. You're allowed to have it on your equation sheet come Monday. But in this case, what I'm going to do is I would like to solve a orbital problem. So let's actually look at conservation of energy and assume that the velocity of some satellite orbiting our Earth is actually, let's say the velocity is 8,650. So
before we keep going, I'm sorry, I spaced a little bit on that last page. I just had a question for that. How do you know when to use, when you plugged in gravity in that last bit for velocity final, how do you know when to use positive versus negative 9.8 for acceleration?
So that's the
gravity,
beauty of the way we write our conservation of energy. It's always positive 9.8. If I had worked it out kinematically, you'd have to pay close attention to that. But with conservation of energy, you just have positive MGH, positive MGH. And then the G is always understood to be just 9.8 without a negative sign.
Oh, because you're giving it a baseline value of the height of the basically energy being the height above the 0 level.
Right. If you allow this thing, if you did call this, for instance, the origin, then, excuse me, I know you can't see the figure now. If you did call this the origin, which is sort of what we worked out, and maybe there was a tunnel over here or something that it fell into, you still would use a positive G, but your H would come out negative. So that would fix itself as well. So yeah, in conservation of energy, you rarely have to think about vectors except for weird things like this. At least in vertical motion, you don't even have to think of vectors, but when you're having horizontal and vertical motion, you've got to work out the details of maybe finding, the velocity at that point so that you can make sense of what that is. Notice if I had said K final was 0, then I'd get an entirely different problem. That's a problem where I shot this thing up at 25 meters per second vertically. But since I shot it horizontally, I had to know, well, it's still going to have some velocity. Hence, I had to put that non-zero velocity there.
Gotcha. Thank you.
No problem. All right, so let's say the velocity is, let's actually say 9,000.0 meters per second at, in this case, we're going to say it is, let's say we're at basically what we call perigee. I'll draw this in a second. At perigee. In other words, when the satellite is closest to the Earth, that's perigee. Okay. And what I want to know is, what is the velocity at apogee? So apogee is the point at which is farthest. So what I'm going to imagine is the Earth is here at one of the key foci, remember. There's an elliptical orbit like this for the Earth satellite thingy. This is the semi-minor, or this is the minor axis. And this, of course, is the major axis. What I'm going to tell you is that this distance from here to here is let's say 16,500 and I'll say that's kilometers. Okay, and this in fact is going to be exactly at the midpoint between it, in which case this distance from here to here is 8,250 kilometers. Okay, and I want to know V at apogee right there. Okay. So by symmetry, I think you can tell that this distance is also the 16,500 kilometers. Okay. So we have the velocity here. It's going to, in fact, be 9,000 meters per second. Now, what I'm going to use is U initial plus K initial. I don't even need the work in or any of those other terms. I'm going to say it's equal to U final plus K final plus 0 plus 0. That's just to save me a little space on the paper, right? So I left out the work in, the work out, and the E loss. And what I know for potential energy is that I have a satellite of mass M, and this is the mass of the Earth, which I know as well. So what I'm going to do is I'm going to say the initial potential energy, which is right here, that's going to be G times the mass of the body times the mass of the Earth over, let's call this distance, let's say RP for R perigee. So that'll be negative RP. And the kinetic energy is going to be 1/2 M times VP.
Is that I forget, is that R squared on the denominator or no?
No, it's when we got it by integration, and that made it into a negative 1/R. So yeah, it's a weird thing that you have the potential energy being a negative, and only as it goes to infinity will it reach a positive, or reach 0, that is. Okay. Over here, we're going to have the same things true. Negative g, the mass of the satellite, the mass of the Earth. Over now, it's going to be 1, 2, 3 times RP. Because remember, this g is measured with respect to the center of the Earth. The center of the Earth is halfway between the semi-major or the middle to the side. So I've got to go 1 RP, 2 RPs, 3 RPs. And then plus 1/2 m VA squared. And that's the thing we want to know. Again, we can wonderfully see that the mass of the object orbiting the Earth is irrelevant because it cancels out. I can multiply through by 2 to get rid of a fraction. That's kind of nice. In fact, I can multiply through by 6 and get rid of all the fractions because there's a 3 down here too, remember? So I'm going to say negative 6 g mass of the Earth over RP plus 6 divided by 2 is 3 VP squared is equal to negative 2 g mass of the Earth over RP plus 3 VA squared, and VA is what we're solving for. So I'll say 3 VA squared is equal to 3 VP squared plus, let's say GM over RP times 2 minus 6. Because this will come over here to be 2 and this will be minus 6. So 2 minus 6. And of course, we're just going to get negative 4 for that. So I will say divide everything by 3 now, and I'll get VA squared is equal to VP squared plus, oh yeah, sorry, it's got to make that a negative now. So minus, now remember I just did 2 minus 6, and that gave me negative 4. Now I'm going to say negative 3 GM over 4 RP. So I can put this in, I'll say 9,000.
Professor, I think you flipped it.
Did I?
Since you divide by 3.
Yes, I divided. Oh yeah, thank you. Yeah, the 4 was supposed to be on top and the 3 was supposed to be on the bottom. Thanks for catching that. That would have been a pain in my butt. Okay, so 9,000.0 meters per second squared minus 4 over 3 times 6.67 times 10 to negative 11. Let's leave off the units because it's getting ugly already. Times the mass of the Earth, which is 5.98 times 10 to the 24 in there. And then all that divided by the radius, or the 8,250. And that's times 10 to the 3 because we're talking kilometers. So that should be able to calculate everything. I'm getting the final velocity squared, by the way. So let's just do that first. I'm going to see 9,000 squared minus, I'm going to do parentheses 4 divided by 3, and then times 6.67 e to the negative 11 times 5.98 e to the 24. And then finally, I'm going to divide it by 8,250 e to the 3rd. And that looks like it did all my math correctly. And that gave me, obviously, VA squared. And that's 16.537. So I'm going to assume I'm using 3 sig figs. So I'll just highlight that they're not. 37 times 10 to the 6 meters per second squared. Okay, so that means VA should be the square root of that. Which is 4.0 665 times 10 to the third meters per second. So basically we went from 9,000 meters per second to about 4,060 meters per second.
I must have missed something. My calculations came out significantly different.
Let's check. I'll do. Anybody else verify my calculations or possibly get what Gavin got?
Oh, wait, no. I input different wrong numbers effectively
Gotcha.
because when I converted the I converted the 8250 kilometers into meters, and then I also converted meters per second and multiplied it by 1,000. Just brain fart, basically.
Okay, gotcha. Gotcha. Yeah, and these are typical orbital speeds. We're talking on the order of kilometers per second is a very typical orbital speed. So this is reasonable. You can see the formula did work out right. Luckily, when I type it in, this calculator shows it to me sort of in that standard form, so I can sort of be confident that I didn't screw up anything with my denominator or anything. So this did come out what I suspect is right. So does anybody have any questions on that? All right, so that is basically the last of the type of examples I wanted to show you for chapter 8. We're done with chapter 8. We will start chapter 9 next time, which is on momentum, and I do know that we will do that next. And then relativity is normally when I normally do relativity right after 9, because chapter 10 is on rotation, and you don't really need rotation to do relativity. So if no one has any questions, you're free to go. If you do, I'll wait for the last person to leave.
Okay, thank you.
You're welcome.
Could you talk to me about the GMM over radius?
Yes.
Like what?
Where that came from?
Yeah.
Okay, so what we did was we calculated the work done, which equals the integral of F dot DL. And we're actually doing it in some sense, we're doing it as if we're taking an object of mass little m from 1 Earth radii to infinity. Okay, so that our DL, which I'm using to point the direction of the integration, is going to be positive dr in the r hat direction, which really just means radially outward. Okay, so again, I could line the coordinate system up such that this is the x-axis, and I just call this dx I hat, and that would work out fine. F, on the other hand, is g m for the mass of the little guy times the mass of the Earth, like this, over the distance away at any point. So that's the F magnitude. Of course, the direction, in order for us to pull it out there, the direction has to be in that positive r hat direction as well. So that's how, and that's r squared, sorry about that. And that's what the F is for this. So when I plug those in, I get work is equal to the integral of g m mass of the Earth over whatever distance you are away squared r hat dotted with dr r hat, which becomes, and we're going to integrate in the positive coordinate direction because I indicated the direction of integration by this guy. So I'm just going to go from r, the radius of the Earth, to infinity. And when I do that, you can see what happens is the G, the M, and the M come out in front, and I get integral dr over r squared times r hat dot r hat, which is just 1. And that becomes G negative G M M times the limit as r approaches infinity of 1 over r minus 1 over the radius of the Earth. You can see the limit as r approaches infinity for this is just 0. So in this case, you actually get G M M over r plus. That's the work done in taking it out. Now remember, work is equal to the negative change in potential energy. So that means the change in potential energy is negative GM M over R. And that's final minus initial. So in other words, change in potential energy, this potential energy here, we're going to assume is 0. And that's the final minus the initial, which means this is all initial. So that implies our potential energy function is negative GM M over R for whatever distance you are from the center. Your book does that derivation on page I think it did it in page, yeah, like page 199, 200, something like that. Does that make sense to you, Gavin?
Yeah, I think so. I was writing some stuff down. I fell behind a little bit around the point you were you wrote about the bit with the limit as R approaches infinity. The capital R sub Earth or whatever, that's just
That's for the specific case
the
where-
initial radius.
Yeah, that's the initial distance from the center of mass of the Earth, which is the center of the Earth, basically.
Okay, so that's and so the work being equal to
The
what is that?
negative change in potential energy. Does that make sense to you? That's a big concept that you need to bite. So for instance,
the negative change in potential. Why is that?
So think about it this way. If well, for starters, we do work done by the system. So if the system expends energy by, let's say, climbing a hill, right? Then what's happened is a positive amount of energy has left the system, but the final potential energy is larger than the initial. So that's why you have to have that negative there, because otherwise it'd be U final being smaller than U initial.
Sorry, say that again.
So it's all
couldn't
about
wrap
what
my
the
head
work
around
is.
that.
Is the work done on the system or by the system? So like when we study the first law of thermodynamics, we're going to say we're talking about the work done by the system, whereas the chemists will say the work done on the system, and they'll have a different sign than we do. So in this case, we actually calculated the work done to the system. In other words, and we got a basically a positive quantity. Okay, that's because we took the work done to the system and set that equal to the change in potential energy, which basically had high potential energy to 0. You know, out here at infinity, when you're infinitely far away, that's 0 potential energy. It's the opposite of when you're close to the Earth.
Because the farther away you have no gravitational pull.
Exactly.
Okay.
So that came out to be a positive amount of work done on the system. What we're saying here is if we do work on the system, that should actually make its potential energy increase. So if we call work done to the system positive, then this negative would require the final to be lower than the initial. So we have to do it the other way around. So if I put work into the system, that should increase my potential energy. Well, my potential energy, the change in potential energy is U final.
Well, I thought you were saying that we were putting work into the system and removing potential because we're making the radius larger.
In this case, yes, we put work into the system because we actually applied a force to the mass and pushed it out that way. Okay. And
Yeah.
that gave us a positive amount of work because we took it from somewhere that it wanted to stay because the earth was pulling it so hard till it was able to escape. Now, since delta U is final minus initial, you can write this as U initial minus U final if you want, and you'd see, oh, okay, well, a positive amount of work would mean U initial is bigger than final. So this must be work done by the system as opposed to on the system. So the work done by the system is the negative change in potential energy. See, if this is positive, then so is this.
I'm sorry, this is kicking my ass. I must be missing something at a lower level or something because I can't like.
Well, you're sort of using a nebula. You're probably using this nebulous idea of work, and you're not really putting much thought into what's doing the forcing and the pushing versus what's being done to your system. So in the case of a planet, we're talking that the planet has a gravitational force that tends to pull things this way.
Yeah.
Okay, if the system, let's say it's a frog sitting on the surface of the earth, if he does some work, because he's the frog, he's part of the system. If he does some work by jumping, then he is actually going to get further away. And if he's powerful enough, he may even be able to escape the earth, right, with strong enough leg muscles. So he's doing work by lifting himself off the surface. Well, that means his final potential energy will be less than his initial potential energy. And
like in an orbital sense, in like a cosmic sense, as something gets further, like so on a micro scale, you jump, your potential energy increases because you're above something. Basically, your height has increased. But on an orbital scale, as it gets larger and larger, it lowers. So I understand that. Like I get that part. So keep going.
Okay, so when I get out here and I do a calculation of U final minus U initial, I get my U final smaller than my U initial.
Final, yeah, effectively U final would be 0 if it was infinite distance.
Exactly. So that should in fact give me U final minus U initial, which would give me a positive quantity. And that's consistent with the frog doing a positive amount of work. And the frog is our system. So that's the only way it makes sense, is when the work done by the system is the negative of the change in potential energy.
Okay, I think I'm starting to get this. So like you're saying that the work done, what was it, within the system?
By the system.
By the system?
Yeah. So,
Right, so
the mass is like a rocket. And
So yeah, it does work
Mhm.
it does work to get farther away from the planet, and by doing work, it decreases the potential energy.
Mhm.
So then the work
Because
is equal
it's
to
losing,
the decrease in potential.
right? Work means you're
Okay, so
losing.
so
energy.
is that just kind of a general rule that the work is equal to the negative change in potential? Is that a general sort of I
Yeah,
guess
this is something that's
guideline
going to be used over
for
and over and over
orbital
again. Yeah,
for orbital stuff?
it's actually just true in general, as long as you're talking about the work done by the system. Because remember, work is another, it's the ability to change energy. So if the system is giving up some work, then its potential energy has to decrease. There's no way around it. Because otherwise it'd be making up energy.
Well, I thought well, and this is for like the macro scale, like, you know, stars and stuff. I thought you were saying that in the case of a micro scale, like you perform work by like throwing a ball up, you are increasing the potential. And is that just like for two different like frame of references kind of deal, like two scales of analysis?
Yeah, so as the ball goes up, it is losing potential energy.
Well,
But
it's
that was a
losing.
result of a person putting work into the system, not the system doing the work. Like if the ball were instead a rocket, it would have to lose some of its energy that was stored as gas and chemical energy. It would have to lose some of that energy to increase its potential energy. So you can sort of think of that negative as a loss.
Well, wait, so then is it increasing or decreasing its potential? Because it's decreasing its like chemical potential by expending fuel, but then also decreasing its potential energy by getting farther from the planet?
It's losing some energy from the system. By doing work, you're taking energy out of the system. Therefore, your potential energy is going to decrease. Right? The rocket only has a finite amount of energy. It's got basically whatever fuel, a chemical energy the fuel has. When you fire it, obviously you're losing some of that energy. Luckily, part of that energy, some of that work done by the system is going into raising the potential energy, but you're still got a net loss of energy.
Okay. Well, and so now you're talking about raising potential. Are we raising or lowering potential in this
In
example?
this case, we actually lowered it on the large scale. Initially, the way it would work is when you're close to the surface of the Earth, obviously you're increasing that small potential energy, that MGH potential energy. But yeah, on the macro scale, it becomes the opposite. Yeah, it's sort of a pain in the butt. But yeah, we'll use this a lot. But the deal is we'll use it when we're calculating the work done by the system as opposed to the work done on the system.
Okay, so generally work is negative change of potential when work is done by the system
Exactly.
versus the other way around for positive change potential.
Yeah, if work's done on the system, then you get positive delta U. That's what happened here. That's why we got a positive GMM dealio.
Okay, and so what would you say is a kind of concise definition of work done by the system versus on the system?
Work done is when the system, work done by the system is when the system is applying a force to something else over a distance. So that F dot DL is leaving the system.
Well, I thought that like the energy is, I guess, potential energy is being reduced. I'm sorry, say again.
Work done by the system is when the system is applying a force to something else.
Well, so something else. What do you mean? Like define something else.
Okay, so a system is just the thing that you're studying. Like in the case of this mass here, that would be just the rocket ship.
It's like the
Right.
mass of the rocket or the satellite or whatever it is. Yeah.
Well, that thing has to do work to get it off the surface of the earth. That thing has to basically apply a force over some distance. And that force in principle is just pushing particles of gas and dust out the rear end very fast in large copious amounts.
Okay.
So
But then like what defines like work done by the system versus on the system? Like you've got the rocket that is expending fuel to perform that work versus like a giant slingshot that is going to shoot the rocket that is work done on the system by something separate.
Or me, a godlike creature, grabbing the rocket ship and applying a force to the rocket ship, not to something else, and pulling it.
But how are those calculated differently? I'm not understanding the difference, because a force is still moving it.
Yes, but in the case of me being a god, I'm applying a force this way. In the case of you, part of the system, you're applying a force this way that makes the object go that way. So it's all about this.
Okay, I guess I can see that.
Yeah, like when you carry an object up a flight of steps, you're applying a force upward and gravity's pulling downward. You're ultimately doing a positive amount of work to the box because your force is parallel to the DL. Gravity, on the other hand, is doing a negative amount of work on the box because its force is down and the object's going up. Well, so that's just the big thing. So and to be honest with you, every time I do this, I have to think through this process again. So, you know, it's not trivial for me either, put it that way. So I have to sort of make sure I make sense of it, because inevitably when I'm using work and potential energy, I have to struggle for a brief second just figuring out what work I'm doing. Am I doing work on the system, or is the system doing work to itself? Because if I'm doing work on the system, I'm adding energy to the system, whereas if the system's doing work to make itself do something, it's taking away some of its energy.
All right, so work being done by the system could be said to be like a rocket being propelled by exerting force opposite the direction of movement, versus work done on the system, like if an outside force is pushing the rocket in the same direction of movement.
Yeah. And it might help you to read, like I said, pages 199 and 200. This is one of those instances where your textbook goes through that. It does it again in the second semester. That's why I told you guys this is sort of important to bite. What I did when I first ran into this problem, I just memorized it, that the work done by the system is the negative of the change of potential energy. And then slowly over years, I've made sense of it and saw how it worked out to give me the right sign and all these problems and derivations that various textbooks would do. So that's sort of your first goal, is just to memorize work done by the system is equal to the negative of the change of potential energy.
Actually, I just see what you wrote down at the bottom there. You said the change in potential is equal to negative GMM over R, and then is also equal to positive GMM over R.
Okay, this was a different
that?
work calculation where I came up with positive. See, this is a negative times a negative, so that makes it positive. This was the work done by that force. Notice this force is pointing that way, and the object went that way. So that was a positive amount of work done. But it was done on the system, not by the system.
Oh no, I was talking about the line below that, where you have
yeah, that's just bad where I wrote something after the fact. So this is
okay,
and that's that.
What is what?
Sorry, it fell out of the
okay, gotcha. All right, those were two different calculations.
Yeah, I drew this after the fact. I should have boxed it off. So I would
Gotcha.
say that you're thinking right. That's good that this is bothering you. Most people ignore it and they will later get it wrong. You, as a first step, should probably memorize work done by the system is equal to the negative change in potential energy, and then mull that over. And every time someone does a derivation with work, pay attention to whether they're saying work done by the system or on the system, or what force is acting over what distance and all that stuff, so that you can pay attention to it. And over time, you'll gain a experience that makes this make sense. Or, I mean, I'm assuming that I'm, a normal person, and therefore my struggles are like every other person's struggles. It might be that I'm slightly not very bright. Maybe it comes easier to other people, but this always was a pain in the butt to me.
Gotcha. Yeah, I'll go and check out those pages. I think I have the e-text. I'll go take a look at that. I'm thinking like I'm starting.
Go ahead.
I'm starting to kind of understand what you're getting at. It's still a little bit nebulous, but I'm kind of understanding it.
Yeah, that's no problem.
I've never had the strongest grasp on like the integration and derivation, and also the dot product thing that I think that's supposed to be something that I know, but I'm taking this course after having not been to college in like 7 or 8 years.
Yeah.
So lower level college math stuff is very fuzzy for me. So that's a little like, what was it? One of the questions on the conceptual was what is it, like the scalar product is or is not distributive, and what else did I write down? It's like it's distributive and something else. It's a weird word.
Is it the I'm thinking of the word and I can't get it out of my head. It's all I'm thinking is
it's a commutative, yeah, distributive and commutative.
Commutative, yeah. Does the order
yeah.
matter is what commutative means.
So order matters.
Yeah, that's what commutative means. All I could think was abelian, and that's like the fancy word. So abelian versus non-abelian, and I wasn't trying to give you that. So yeah, I couldn't come up with commutative either.
And then so what does distributive mean?
Distributive means like A times left parenthesis B plus C right parenthesis is AB plus AC. That's distributive property.
AB plus AC, you said?
Yeah, A times a binomial B plus C is equal to AB plus AC.
Yeah, like the question said those words, and I didn't even understand what those words meant. It's been a long time since I've seen something like that.
That's a very normal thing. Unless, and even me, I mean, I stay up pretty current with math, but I just forgot the word commutative myself. So yeah, that's the normal thing. And it was
Gotcha.
Worse is there's other words for it, and then you might remember one, and you don't want to give that to a student. But you don't want to know abelian.
Yeah, it's kind of funny, some of the terminology here for like the orbital stuff I'm actually familiar with because I played a game called Kerbal Space Program. You ever heard of that?
Yeah, and actually Mario Universe or something like that does another one.
Do they talk about like periapsis and apoapsis and stuff?
Yeah, they do some of that crazy stuff too. So it's kind of neat. But
actually,
yeah, Kerbal I've heard a lot about.
I was wondering about that. You said perigee and apogee, and I have heard the term periapsis and apoapsis. Are those the same or what?
Yeah, it's just when you put the cis on the end, that means relative to anything. When you put the G, that means geo or Earth. And when you put the helion, that means Helios or sun. So aphelion,
okay.
Perihelion, apogee, perigee.
Okay, so the cis at the ends, the apoapsis and periapsis, those are just in relation to whatever body it is orbiting.
Exactly.
Okay.
Closest
I
approach is
remember
when they're a
right.
pair, and apogee is when they're furthest apart. Our ap is furthest apart.
Yeah, I ended up learning like or basically wrapping my head around the just the idea of orbital mechanics in general, like when to apply a force to cause the what do you call it, to cause the orbit to
change.
extend in whatever direction you wanted based on where it currently is in the orbit and stuff, playing
Right.
that game. It's very fun simulator.
Like if you're following a satellite that you want to catch up with, your instinct is to speed up, but that's actually going to mess you up because that'll make you drift out and you'll slow down. So you should really slow down. That'll drop you down to a lower orbit, which causes you to speed up. Also conservation of momentum. And then you end up right up under the satellite, and then you can speed up and have the satellite come in your craft. So yeah, that's one of those backwards things. And they get that right. Like on some of the movies, like Apollo 13, they do it, mostly correct in there. They got the size of the moon wrong, but they handle the orbital mechanics right.
Yeah, well, I mean, I think they made them much smaller, just mass speaking, just to make it easier to actually get off the planet. Because there are there are mods that change the mass of the the
planet,
Earth, Kerbin, and then Moon to make it significantly more difficult.
Yeah.
But it was very interesting. But yeah, thank you for the explanation. Staying late, that was very helpful.
No problem. Hope it helped. Have a good one.
You too.
See ya.